And thanks to the organizers for inviting me to give a talk here. So yeah, I'm going to talk about isospin-dense QCD matter. And really the context for this is thinking about QCD in extreme conditions. So understanding the QCD phase diagram when you add chemical potentials or temperature or magnetic fields is of course a very important challenge for theory. And really you can think about it as really trying to understand the phase structure of QCD matter, and this is like comes about in terms of understanding the equation of state. So QCD in extreme conditions governs the early universe. It governs the interior of neutron stars and supernova. And this is just a picture from some report recently of kind of what we know about various aspects of this as a function of temperature, baryon chemical potential, and isospin chemical potential. And you can see that much on this plot is unknown, particularly in fact that some things over here are just not correct anyway. Right? So what do we know about this? So of course, along the zero chemical potential axis, just looking at finite temperature, we know from Lattice QCD that there is a deconfinement transition that with physical quark masses is a crossover that occurs at about 155 MeV. And this was shown roughly 10 years ago by the Hot QCD and the Budapest-Wuppertal collaborations. Looking along the baryon-dense axis, this is something where we know much less. So perturbative QCD tells you things about asymptotically large baryon chemical potential. There is some information coming from phenomenology of nuclear structure at very small chemical potentials, and there are some things you learn, for example, from LIGO's observation of neutron star mergers, but there's really not that much going on. And so this plot really shows what we know, perturbative QCD out here somewhere, some nuclear physics down here, and this region in here is entirely an interpolation, and the question really is how model dependent is what we do in that interior region. And so in this situation, any rigorous constraints that you can place on this are going to be very valuable. So Lattice QCD is not directly applicable because this is something where you have a measure that is complex, and so you can't do Monte Carlo for this. So there's a sign problem. And yeah, really, so I colored this axis red. Okay. Third axis here is isospin chemical potential, and this is what I'm going to talk about today. So this is kind of a summary of what we'll discuss. So this is a plot of the speed of sound mapped out over basically the entire range of isospin chemical potential. We can measure a superconducting gap along this axis. And in fact, what you can learn along this axis constrains everything in this plane here, in particular along the symmetric baryon axis. Okay, so let's turn to isospin chemical potential. So the phase diagram of this was conjectured in a very nice paper of Damson and Misha Stefanov in 2001. And it's really characterized by condensates at low temperature. So if you increase the isospin chemical potential above m pi in my units, sometimes people use units where this is m pi over 2, you find a condensate of pions, basically a Bose-Einstein condensate. From perturbative QCD at asymptotic densities, you know there is a BCS superconducting state that forms with U d bar Cooper pairs. And somewhere in between, there's kind of a crossover between these things. But exactly what happens there and where or if there is a breakdown of this deconfinement transition, or whether it goes the whole way through, is not known. Okay. So as of about 2023, there have been a number of lattice calculations that had taught us about this system. So with isospin chemical potential, the measure of the path integral is real, and so you can do the Monte Carlo. And I'll come back to that in a moment. And so this is kind of a cartoon of what's known from these calculations by Brandt, Katerian, and Drodian, a couple of other people. You know something about the steepness of this line here as a function of temperature, and about the turnover, but not that much. So what I'm going to talk about is really going to be at very low temperature, vanishing temperature, as a function of chemical potential pretty much the whole way across here. Okay, so how do we deal with isospin chemical potential? Well, as I said, you can add a chemical potential to the action here, and in QCD, this remains a positive definite measure, and so you can do Monte Carlo. However, for every choice of the isospin chemical potential, you need to do an entire new Monte Carlo calculation. So it's expensive, which is why you see in this plot that there's not a lot of points on this. Okay. So another way to think about this grand canonical approach is really that this partition function is determined by this sum over states of the beta is the inverse temperature, the energy of states, and the isospin charge here. Okay. In the low temperature limit, so beta large, this is dominated by the ground states, and then it's dominated by the maximal Z component of isospin charge states. Okay, so you can really restrict this sum in that limit to the ground states with the maximal isospin charge. Another way to think about this problem is go to a canonical partition function where we fix the isospin charge, you get a sum over states there. And of course, from that, from measuring energies as a function of the isospin charge, you can construct the chemical potential. Okay, so in these, apart from this top approach where you add the chemical potential to the action, what you need to evaluate these is really understanding the energies of states with fixed isospin charge for a large number of isospin charges. Okay, so let's think about one way you might do that, and that's by using taking zero temperature, zero density lattice QCD ensembles and measuring correlation functions on them to extract energies. So if we think about something that gives us isospin charge, the simplest thing you might do is take like a pi plus interpolating operator, so something that adds isospin charge to the system, and then I want to add a lot of isospin charge, so I can raise that operator to some large power, and that gives me something that has that will probe states with the quantum numbers of isospin n. Okay? And the large time behavior, assuming an infinite temporal extent, is going to be dominated by the ground state energy of that charge. However, you might say, well, that's kind of crazy, because if I think about n being large, then putting all the quark fields in here, the number of Wick contractions I have to do is n factorial squared. And so if I want to get to something like n of 6,000, I have 10 to the 40,000 Wick contractions, which we are never going to do. Okay, so this is a problem that I've been working on with various people for a number of years. And previously, we'd actually managed to use various tricks to get to isospin charge about 70. Basically, the algorithms we came up to do this were limited by their cost, so the best algorithm scaled like n to the fourth, and by the need to have extreme numerical precision in the calculations, going to basically, as you increase the charge, you have to increase the numerical precision with which you do all of the calculations. And so we found a way of getting around that. All of these methods were based on basically thinking about an object that you construct from a quark propagator from some point to somewhere else, and then another quark propagator coming back. And this is a pion because there's a gamma 5 sitting here. This thing you should really think about as a matrix in space, spin, and color. Okay? So it's a 12, L is your spatial dimension, so 12L cubed by 12L cubed matrix. Okay? And it's projected to zero momentum at this other end, but it's left free over here. Okay. So it turns out that there's a way of writing these contractions in terms of symmetric polynomials over the eigenvalues of this pi object. Okay? I won't prove this, but it's something that is shown in here. I'll just give an example of how this works. So these symmetric polynomials of the eigenvalues are all products of n of the... so if we have a matrix of size n, then we take all products of the eigenvalues to get the n charge, the lowercase n charge state. We take n of those eigenvalues and take all possible products of it. So a nice thing about these is that there's a recursion relation that you can write down to generate these symmetric polynomials, and this only scales like n squared. So the whole cost of this algorithm is basically finding the eigenvalues of this pi matrix, which is an n cubed operation, and then this is essentially free. So just as an example, thinking about a 3-pion correlation function, so each of these points is basically a u bar d or a d bar u operator. There are 3 different kind of Wick contraction topologies that come out of this. So there's things like this, there's things where it does this, and then there's this most complicated one. If you think about this is this pi matrix here, and now I'm contracting the spin color space indices here, so I get a trace of pi, trace of pi, trace of pi, so I get a trace pi cubed. Okay? This one here is basically, here's a pion block, here's another one, and this is just a matrix product of them, so you get a trace of pi squared times trace of pi, and if you're careful, you get a factor of 3 on this with a sign, and then this one is trace of pi cubed. Okay? So now we can work in terms of the eigenvalues of pi, and so trace of pi cubed is just, here's the trace is just the sum of the eigenvalues, cube it. Here's trace of pi squared, so it's the squares of the eigenvalues, blah, blah, blah. And so this expression looks kind of messy. Here I'm working with capital N is 4, so I only have up to 4 here. And so if you look at this and expand it out, it turns into this, which is this symmetric polynomial of the allowed 3-term eigenvalue expressions. Okay? And so that's something that generalizes to arbitrary capital N and little n. So using that, we're able to study these energies as a function of the isospin charge. So over the course of a couple of years, we've done a calculation using 2+1 flavor QCD, 4 different lattice ensembles here. There are 2 different lattice spacings. The pion masses go below the physical value and above it. The box sizes are kind of fairly decent for these pion masses. I'll point out that, for example, this box here, so 96 cubed by 192, what we're going to do is to get to 6,144 pions, we essentially have to put quark fields on a 8 cubed grid of sites within that 96 cubed grid. So if you think about the density of pions within the system, it's basically 1/12 cubed sites are being occupied. So it's not anywhere near sort of saturating the degrees of freedom of the system. Okay. So just a technical point is because we're looking at just the light quarks of this system and our U and D are degenerate, this pion block is actually something that looks like S dagger S, so I can do an SVD instead of an SVD of the propagator instead of an eigenvalue decomposition of this thing, which is just numerically nicer as well. And to make sure everything's working, we do this in multiple different numerical precisions, and everything does work. So this is just a plot of the eigenvalues of the nth eigenvalue for n of these values for one background gauge configuration. You can use those to build the correlation functions using this symmetric eigenvalue algorithm. And this is the correlation functions computed. And this is kind of an interesting plot because this is the log of the correlation function, which you see is falling exponentially, and then because of the periodicity of the lattice, it goes back up. This is a log plot, but the units here are in 10 to the 4. So this is falling by 250,000 orders of magnitude across my calculation, okay? Which is an interesting challenge to deal with. There's kind of some interesting technical things that happen. So the correlation functions vary very, very rapidly between the samples, right? Every gauge field you have, like fluctuations are going to be enormous. And this really means that the central limit theorem is only going to be valid at absolutely unachievable statistics. Okay? However, these plots here are plots of the log of the correlation function. This is for 500 pions, this is for 4,500, and each of these peaks is a different time separation of the source and the sink. So you can see these things look pretty normal when I plot their logarithms. Okay? And what we can do is assume log normality of these distributions and incorporate deviations from it by doing a cumulant expansion. It turns out that we actually can't measure a deviation from log normality in this system at the statistics we have. So basically everything I will show later is assuming log normality, but we have the backup that we know what the cumulants are doing. Okay, so if you make that assumption, you can get an effective energy as a function of time from the mean and the variance of that log normal distribution. So this is basically something that asymptotically, if we had an infinite temporal extent, would plateau to the ground state energy of the system. Of course, we don't have an infinite temporal extent, so the boundary conditions change that. So you get something that's dropping, plateauing, and then becoming periodic around the boundary. And so this is on one of these ensembles. This is on the 4 different ensembles, and you can see that certainly for the longer temporal extents, you really do see this flat behavior for some regions. So you are seeing the ground state extraction. The other thing that comes from this very large variation between samples is there's no sense in which I can really think about doing like a fit to this region because the different time slices are many different orders of magnitude. So you have to do something slightly more complicated in sort of propagating a bootstrap distribution of the samples that extracted in some window, which is what we do. But if people want to ask about that, I can discuss it later. So these are the many pion energies as a function of the isospin charge on the 4 different ensembles. So this is the smallest volume, and this is the largest volume, and this one has the lighter quark mass. This is actually the isospin charge times the pion mass. And so you see most of the energy of this system is in the interactions. And so for these maximally charged states, you have basically multiple pi plus interactions which are repulsive. As an interesting fact, on our smallest lattice, we get basically an LHC worth of energy in our system. So you can construct the chemical potential from the difference of this for different isospin charges. And down here, 3 of those 4 ensembles are plotted, the chemical potential versus the density. And you see there's a curve collapse that happens. So we really think we understand that we're getting to the thermodynamic limit. And in these calculations, the temperatures are of order 20 MeV. So they're really pretty close to 0. This also shows chiral perturbation theory, which we agree with at small densities, and this is the Stefan-Boltzmann expectation, which you see asymptotically agreement with. Okay. So you can then construct more complicated observables, basically using this. So for example, the pressure we can construct here. So this is, again, the 4 different lattice ensembles, and also in red, there is the continuum physical quark mass extrapolation / interpolation that we can do. And the orange band here is next to the leading order perturbative QCD with a pairing gap turned on. Okay. We'll come back to that in a moment. Just for the lattice people in the audience, so the extrapolation to the continuum limit is shown here, and the interpolation to the physical mass is shown as this thing here. we basically use a whole bunch of different extrapolation interpolation forms and then do some model averaging over the possibilities, weighted by how good the fits are for them. Okay. As I said at the start, we're able to determine a superconducting gap. So the way that we do this is from asymptotic freedom. You know that for asymptotically large chemical potentials, you have an attractive interaction, so you're going to have superconductivity. And you can compute basically the gap as a function of chemical potential as an expansion in the coupling, but it has this kind of non-perturbative form here. From our point of view, we can you can basically do a perturbative QCD calculation of the pressure in the with the gap turned on versus it turned off, and that is given here. This is in this work by Fujimoto. And so one way of non-perturbatively extracting, or partially non-perturbatively extracting the gap, is to look at our lattice QCD calculation of the pressure minus perturbative QCD with no gap, right? And if we're in a regime where perturbative QCD is valid and the lattice calculation is valid, you get an extraction of the gap. And that's what is shown here. So the red band is exactly that. So this is the lattice QCD minus this piece here, the extraction of the delta from this. And you see that this is separated from zero. It agrees with perturbative QCD, although the uncertainty on perturbative QCD from variation of the scale by a factor of 2 is really pretty large. But this ends up giving you a gap of order a few hundred MeV at chemical potentials of 1 to 2 GeV. So looking at the energy density is interesting. You see the same curve collapse when we look at the calculations with the same mass. That's the 3 A, B, and C ensembles, and then the D ensemble and the continuum extrapolation, which is a very similar mass, shown here. This peak is really showing the onset of the Bose-Einstein condensate, and you can see chiroperturbation theory for the two different masses is these two dashed curves here, so you basically see agreement with that. And then asymptotically, you see, again, the approach to perturbative QCD. Okay, this is the speed of sound, and this is kind of a messy plot, but you see all of these things are collapsing onto top of each other, so we really can extract from this a continuum physical mass thing. Importantly, this turns over rather than becoming large, and it passes through speed of sound squared divided by c squared of a third, which is a bound that's being conjectured in various contexts. And so this, in fact, has also been seen in two-color QCD by Etsuko in work in the last couple of years as well. Okay. So we can then take the lattice QCD information, which is valid over some range of chemical potentials. That's indicated as the red stuff here. When we go to very small chemical potentials, we're basically asking about very, like 1, 2, 3 pion systems, so we're really not thinking we have very good thermodynamic control there. However, chiroperturbation theory works there, and so this blue band is chiroperturbation theory with an error coming from looking at next to leading order versus leading order calculations. At large chemical potentials, perturbative QCD turns on, and so we have a bound, like a range of values coming here from perturbative QCD, with the yellow band being the scale variation there. And importantly, there's kind of overlaps between the lattice QCD here and chi-PT and with perturbative QCD here. So we basically have the entire chemical potential axis mapped out. And based on those three pieces of input, we can build a Bayesian model that's sort of valid everywhere. But since the things are overlapping, it's really kind of a fairly simple thing to do. However, it is something that in the context of the nuclear equation of state is the way that people really think about what's going on there. If you take perturbative QCD without a gap, then you actually find that the lattice result which is here, and perturbative QCD without a gap is this thing down here. There's some weird discontinuity that has to happen unless you go to very large chemical potentials before the perturbative calculations become valid. So you need to go to something like, what's this about, I don't know, 5 or 6 GeV before that can happen. Okay. So this is showing what happens if you don't use the lattice QCD input in this Bayesian model mixing. So if you make the kind of simplest assumptions, and these are kind of characterized by a length scale of how much in this horizontal axis, how much you propagate the information you actually know. So from this yellow band, how does that influence how you interpolate here? So this is kind of a mild assumption, and a more constrained assumption is this one here, which is this, right? And this is kind of what people do in the nuclear equation of state. They impose a fairly high degree of correlation between what you know and the region you don't know. And you might get this band here versus a low degree of correlation where you get this big gray band here. You see that if you do this, you actually disagree with the lattice result in the middle here. So this is kind of a cautionary tale for looking at non-zero baryon density. Okay, but that's what I want to say about the isospin chemical potential axis. Hopefully I've got a few more minutes, right? Okay, good. I'll be done by then. So yeah, I think with a combination of lattice QCD, chiral theory, and perturbative QCD, for zero temperature, we really understand the phase structure that's going on here. Okay. So let me turn to the nuclear equation of state and to QCD inequalities. And this is something that was first thought about by Tom Cohen 20 years ago. So if I look at the two-flavor partition function for baryon chemical potential, then I have, this is my partition function, and I'm assuming my two flavors are degenerate in mass and have the same chemical potential here. Okay? And as I said before, this determinant is now complex, and so you can't do important sampling Monte Carlo. If I look at two-flavor isospin chemical potential, then I have the same thing, except one of the determinants has minus the chemical potential of the other one. Okay? And so that you can easily show that corresponds to the absolute value squared of the determinant with mu, as mu I over 2 is its chemical potential. And so comparing this expression and this expression, and just doing simple Cauchy inequalities, you can see that this system, the chemical potential, the partition function for this baryon charge system is bounded from above by the isospin partition function for an isospin chemical potential that is 2 times the baryon chemical potential divided by NC. Okay? And so since logarithms are monotonic, we can take this bound and write it in terms of a bound on the pressure. So the bound on the baryon system, the baryon dense system, is bounded from above by the isospin-dense system with some rescaled chemical potential. It turns out that this relation is actually saturated up to 3 loops in perturbative QCD, but it's something that is valid no matter what the coupling is, right? So we can then use this to use what we've learned about this side to constrain that side. And so this is a plot for symmetric nuclear matter now of pressure versus the energy density. And the various curves here are phenomenological equations of state coming from nuclear physics. From perturbative QCD, you essentially know this equation of state has to connect somewhere up into this top corner here. And the constraint from the isospin chemical potential really, it rules out everything outside this strangely shaped red region. So chemical potentials that can be over here are just not allowed. There's also causality that gives some of this constraint here. Okay. So this isospin-dense system, somewhat unfortunately, doesn't rule out any of these equations of state. It'd be great if it had, but it's a model-independent, rigorous bound on what equation of state could be. Another way of looking at this bound is to look at the pressure. So now I've taken the pressure in our calculation of isospin-dense matter. Here is a pressure versus chemical potential plot from nuclear matter, again with this big interpolation region in the middle. And now I want to translate these to be on the same axes. So you can see from this axis, this is already very different units than are coming in the isospin-dense system. But we also have to translate the baryon to isospin chemical potential. And so the baryon plot I've actually shrunk and kind of put in the right place here. In fact, perturbative QCD tells you that these two things do the same thing at up to 3 loops out here, so that they should kind of overlap. But you can see that the isospin pressure for a given chemical potential is considerably larger and really is not, as I said, is not materially constraining what's going on in the baryon-dense system. Okay. So that brings me to the end. So we have now a complete determination of the isospin-dense matter equation of state from using lattice QCD, chi-pt, and perturbative QCD. We see the transition to the BEC, and we see the superconducting gap from this difference between the lattice calculation and perturbative QCD with no gap. The conformal bound of speed of sound squared less than a third in units of the speed of light is clearly exceeded, as it is in two-color QCD. We have these rigorous bounds on symmetric nuclear matter, and they also translate into real nuclear matter as well. And in the process, there have been some fairly interesting lattice calculations, developing new algorithms to look at many-body systems. Seeing kind of crazy things where the central limit theorem is never going to be useful for these calculations, and doing analysis based around this empirically observed log normality. Thank you.
Okay, we have time for some questions.
Yes, thanks for a very interesting talk. There must be some intermediate regime where can you describe this by some kind of cue ball? Like it's just a configuration of a charge scalar field?
Kind of in this picture here, right, really?
This somewhere region.
I mean,
it doesn't know about asymptotic freedom, but...
this is very different than the baryon-dense phase, right? So, I mean, basically, the whole way across here, the objects are really, they're pions in some sense, except they're more extended over here, right? They have some, the color is contracted across this Cooper pair, but they're delocalized. But they have the same quantum numbers.
But this quasi-classical description by cue ball, maybe it predicts something interesting about speed of sound, or
I haven't seen
has anyone looked at this?
That way, but maybe.
Okay.
Okay. How convenient from your Arkady is.
It's kind of maybe unneeded deviation, but still, when you have this average of, say, U bar D, right? I'm wondering about, say, higher the spin. Imagine that you have like a 4 fermion with a higher isospin or whatever.
Yep.
I mean, not quadratic. I mean, is it possible to? I understand that it maybe it's a little bit exotic, but still.
Yeah, I mean, so you might ask, so what is the ground state of this system at these large densities? I don't know the answer, right? I mean, all I do is probe the system with particular operators, and the eigenstates of the system are what they are, right? They are clearly not anything close to n non-interacting pions. There's interesting questions you might ask is, how can I probe what the structure of this system is? And so one thing that we're thinking about trying to do is really sort of test whether, for this condensate, whether you see any kind of separation dependence of this. So do you see things where there is correlation over some non-zero distance for this? Another thing you might try and do is not use these interpolating operators that are many pions, but make like things that have more exotic structures. And yeah, in principle, you might learn something doing that. We haven't done that.
Okay, thank you.
Sure.
Other questions?
Thanks for a very interesting talk. So I have a question is, if there's a study of the isospin-dense state out of equilibrium, and what kind of a method is possible there?
So not with lattice methods, that's for sure. So as I said at the start, there are some studies that look at finite temperature, but not non-equilibrium systems. So I don't know.
Is there any studies? Or?
Not that I can think off the top of my head, at least.
Okay, thanks.
So in your computation, you start from canonical ensemble and perform Legendre transformation to ground canonical, right?
Yeah, that's one way of thinking about what we're doing. Yes.
Yeah, and in that case, in large mu I, or if mu I is larger than m pi, we are having pion condensation and spontaneous symmetry breaking occurs, while canonical ensemble always seems to preserve U1 symmetry. And do we have some subtlety when performing that transformation numerically?
So, I mean, it's really a question of, it's really a question of how you get this coming out, right? So yeah, you might ask, how does that symmetry breaking come about from the combination of all of these different terms at some level, right? So the ways this might break down, I think, is if there's some reason in which I don't get to truncate this with the ground state, right? So, I mean, of course, up here, this is the sum over all states with this particular isospin charge. I think from kind of a pragmatic point of view, the fact that we see all of these curve collapses means there's no, in practice, issue. But for example, another thing we're trying to do is include the first excited states in this thing, just as a way of checking that. But yeah, I think pragmatically, there does not seem to be a problem.
It looks okay, but I'm wondering why it's okay.
Yeah, yes, I do too.
Other questions?
I just had a naive question. When the central limit theorem fails, why is it log normal?
This is a really interesting question.
You just observe it.
Yeah, so if you think about where log normality comes out, it's basically if you take many products of normal distributions, you will get a log normal distribution. And so the correlation functions, if the fluctuations are independent at each time slice, which they're not, but assume they were, then you would get something that's basically log normal. You should talk to David Kaplan about this too. He spent a lot of time thinking about this log normality. But yeah, it's empirically observed in these things.
Could you say a bit more about how you do the fitting?
Sure. So we don't fit, is the short answer. And that's really because, basically because between different time slices, things are just changing so much that basically a sample that dominates on one configuration won't be at all relevant on one time slice, won't be relevant on the next one. And that's kind of the technical reason why this doesn't work. So what we do is we find a window in which this is, or like, I like looking at this one because it's clearly flatter. Over this region in which it's flat, we essentially randomly choose on each configuration, randomly choose a time slice, take the value from that configuration on that time slice, and then make a histogram of all of those, and then propagate this histogram through the whole rest of the procedure.
Another question. So returning to the issue of operators, I mean, how sure are you that you actually have found the ground state? I mean, we know with few nucleon systems that's a challenge. Yeah.
Yeah, no, I'm as sure as you would be if you were looking at a single pion correlation function and you saw this. You would probably argue you had the ground state. Whether you do, I don't know, but like, I mean, yeah, lattice QCD is always variational only, right? So,
as less expert in this, I'm tempted to ask, this kind of plateau, why don't you do multi-exponential fits? And why isn't that a better way than this plateau? I always wonder this. This is the standard
yeah,
thing.
So in this particular case where you have these correlators that are extremely varying, doing a multi-exponential fit would basically, between each of these points, you would just connect the dots, essentially. There's no sense in which I can really do a fit to this data.
No subdominant term you can subtract to get the plateau?
No. I mean, it's basically because of this lack of normality, I mean, if you look at this, you might say, well, this is some excited state given contamination, right? And yeah, I think it is, but like as a technical aspect of doing a fit to this, the lack of the central limit theorem basically means that you can't. Or at least this region here, your fit, if you put in an excited state, it will have no effect in this region. It will do something in here, but it wouldn't give you a better determination in this region. Yeah. Which if you had normal distributions, it would, right? So it makes sense to do that. But in this kind of extreme limit, it's not helpful.
Thanks for the nice talk. You mentioned the saturation of the baryon chemical potential from the isospin through 3 loops.
Yep.
Is it known to break down at 4 loops or suspected or?
Sorry, at 3 loops, there is a term that's different. So that's being computed.
It already fails
Yep.
saturation at 3 loops.
Yeah, there's one diagram that's different between the 2 theories there.
Other questions? Maybe I have a short comment. The speed of sound squared being greater than a third can already be seen in chi-pt. So I'm not so surprised by that second bullet point for whatever that's worth.
Yeah. I mean, chi-pt, like this is NLO chi-pt. So how far you believe that it is valid.
Okay. Let's talk more later, but okay, let's talk more later.
Sure.
Yeah. I think you can see some of it. It depends on some parameter choices, but I think you can get a speed of sound greater than a third, even where you believe chi-pt.
Yep. Okay.
No. It approaches 1. That's the point. It approaches 1. There's a parameter scaling limit that was noticed in the original papers on the speed of sound bound, which are some of my youthful indiscretions, which mentioned that. So, whatever that's worth. Okay. Other comments, questions? Oh.
Sorry, it's a very naive question. Is there some way you could imagine realizing this state?
That's a really good question. So there is, some people talk about pion stars, where you basically have gravitationally bound large isospin charge objects that you can think of as a whole bunch of pions being compacted together. I'm very skeptical that there's any astrophysical situation in which that can happen. Some other people are less skeptical, but we certainly haven't seen one.
Oh, okay, one more question.
Yeah, so talking about applications, I think you might talk to dark matter people, because I have heard discussions about if you have a confining gauge theory in dark sector, then the hadrons of that theory might be candidates for dark matter, right? But the scale of that theory, it's dark, so you can set it to whatever. There are some bounds, but then you can have these pion condensates as a dark matter halos in the galaxy, so then it might be applicable.
Yeah, actually, in my past life, I've done calculations of two-color QCD for kind of dark matter applications, and there, the same algorithm that does many pion systems in real QCD does many baryon systems in that theory, right? So it's kind of neat.
Okay. So I don't see other questions, so let's thank Will again for a wonderful talk.